All right, welcome back. This will be our next lesson for the Google Machine Learning Engineer Associate exam. Before we get started, hit the like button, subscribe, and share. So let's talk about the next set. Problem types and data organization. This is classification, regression, and clustering. Understanding problem types determines algorithm selection, evaluation metrics, and ultimately which GCP services you leverage. Classification. So this assigns instances to predefined categories. The output is discrete, a cat or a dog, spam or legitimate, approved or denied. Binary classification involves two categories: multi-class classification, which handles multiple categories, and then the key characteristics. So you're predicting membership in a finite set of classes. In Vertex AI, classification problems use metrics like accuracy, precision, recall, and F1 score for evaluation. Okay. Then we have regression. So regression predicts the continuous numerical values. The output isn't a category, but a number along a continuous scale. Take, for example, $342,000 for a price of a house, 87.3% for a test score, 2,847 for expected sales for the day. A regression model will learn a mathematical relationship between the input features and output values. In GCP, regression performance is measured using metrics like mean squared error, MSE, root mean squared error, RMSE, or mean absolute error, MAE. Then we have clustering. So clustering discovers natural groupings without predefined categories. Unlike classification, where categories are known upfront, clustering algorithms decide how many groups exist and which instances belong together. The number of clusters, K and K-means, becomes a hyperparameter requiring careful consideration or experimentation. BigQuery's ML K-means implementation makes this accessible through SQL syntax. So we'll go through a little bit about training and validation. Okay, so training, validation, and test sets, right? This is the foundation of a good evaluation. So data splitting represents one of machine learning's most critical practices. Using the same data for both training and evaluation produces optimistically biased estimates. The model has already seen these examples, so performance appears artificially high. Proper data separation ensures honest assessment of generalization performance. So here's a training set, right? Let's say it's typically 60% of the data. This is where the learning happens. The algorithm can adjust its internal parameters to minimize prediction errors on training examples. For neural networks, this involves backpropagation and gradient descent updating millions of weights. For decision trees, it involves finding optimal splits that best separate classes or predict values. Then we have to learn about validation set. So this will be about 10 to 20% of the data. So this will be used during the model development for hyperparameter tuning and model selection. After training on the training set, you evaluate the performance on the validation set. This provides an unbiased estimate during iterative improvement. If performance is poor, you might adjust the learning rate, add more layers, or try different regularization. Then retrain and reevaluate. The validation set guides these development decisions. Then you have the test set. This is about 10 to 20% of the data too. This is reserved exclusively for final evaluation after all development completes. This set is never used during training or tuning. It's your held out data that reveals true expected performance on completely new data. Only after you've finalized your model do you evaluate it on the test set. This provides honest assessment of how the model will perform in production. So why does this matter in GCP? When using Vertex AI AutoML, you can specify data splitting ratios. So the platform automatically handles the separation and ensures validation and test sets remain properly isolated. For custom training jobs, you're responsible for splitting data before training begins. Many practitioners use Google Cloud Storage with organized folder structures. So you can go into your project, set it up, and name it correctly for train, test, validation, okay? And then for cross-validation, this will be the k-fold cross-validation, which will extract more values from the limited data by systematically rotating which portion serves as validation. The dataset is divided into k equal size folds. Training occurs k times, and each time uses k minus 1 folds, right? Or k1 folds, right? For training, and the remaining fold for validation. This technique provides more robust performance estimates when data is scarce, though it increases computational costs. Okay, so that's going to be it for this lesson. Before we get out of here, hit the like button, subscribe, share with anyone you know interested in taking the Google Machine Learning Associate exam. Thank you and have a good day.